Look at a massive old-growth forest. It looks permanent, but zoom out on the timeline, and all that towering biomass eventually collapses into rotting wood. We're often told that planting trees is a fix for the carbon crisis, because living plants actively pull CO2 directly out of the air to build their trunks and leaves. But this diagram shows a hidden flaw. When plants die, decomposition kicks in. Microbes consume the wood, releasing up to 90% of stored carbon back into the atmosphere. The soil organic matter is a short-term sink, holding on to carbon on a ticking clock. To lower the amount of carbon in the sky, we cannot rely on nature's default loop. We have to physically intercept that decaying plant matter and stop biological decomposition before it starts. Biology alone is insufficient to trap carbon permanently. By intercepting the decay process before the gas escapes, we can achieve reverse coal mining, putting solid carbon back into the earth. That interception starts at the farm. Instead of letting agricultural waste and manure rot, this biomass is diverted into specialized facilities. Inside these facilities, the waste undergoes a process called pyrolysis. This involves baking the organic matter at extreme temperatures, often well over 700 degrees Celsius, in a strictly oxygen-limited environment, preventing the material from catching fire. The black substance that comes out of this oven looks exactly like charcoal, but the engineering intent is different. Charcoal is baked at low temperatures, specifically to keep its high energy density so it can be burned for fuel. While charcoal breaks down releasing gas, high-heat pyrolysis reorganizes biomass into a stable, graphitic carbon lattice. Because carbon atoms lock into this specific arrangement, biochar resists biological decomposition. Microbes cannot break it down, locking carbon away for centuries. By shifting our engineering goal from producing fuel to creating permanent storage, we turn agricultural waste into a geological asset rather than a greenhouse gas liability. To see what happens when that asset goes back into the earth, we need to look at the microscopic architecture of buried biochar. At a microscopic level, biochar acts like a rigid, highly porous sponge. Its internal surface area increases the soil's ability to retain water, protecting crops during severe droughts. This shows cation exchange capacity, or CEC. Biochar's alkaline surface binds nutrient particles, preventing fertilizers from washing away, making minerals like phosphorus highly available to roots. Simultaneously, these deep cavities serve as physical bunkers, shielding beneficial soil bacteria and fungi from larger predators. However, this high absorption creates a conflict. Spreading fresh, raw biochar directly onto a farm acts like a dry sponge. It rapidly pulls water and nutrients out of the dirt, reducing immediate crop yields. To bypass this, agricultural engineers use a process called charging. Before the biochar ever touches a field, it is mixed with compost or organic fertilizers to saturate its microscopic absorption sites. Properly charged biochar functions as a permanent, microscopic life support system for the soil. For years, the bottleneck was the production process itself. Traditional biochar production was slow, energy-intensive, and prone to emitting dirty exhaust gases. This schematic details a breakthrough announced in July 2026 by researchers at the Hefei Comprehensive National Science Center, reaching the scale required for industrial production. Their one-step catalytic dry carbonization process utilizes a single high-pressure reactor capable of generating over 50,000 tons of high-value biochar every year, achieving high yields with low emissions. Modern facilities also include an additional layer of capture. They manage the exhaust gases from these reactors, which carry a dense concentration of CO2. In this diagram, you can see how that exhaust is managed. The flue gas contains roughly 20% CO2, hundreds of times the concentration found in the atmosphere. By routing this gas into mineral weathering capture systems, the amount of gas trapped in rock is added to the solid carbon stored in the biochar, increasing the net negative balance of the facility. We are pulling atmospheric carbon down, baking it into an indestructible matrix, and using it to revitalize the topsoil that feeds the planet.